Hello, today we are going to be dealing with projectile motion. Projectile motion. Now, projectile motion it's actually a category of kinematics, right? It's a category of kinematics. Now, in kinematics at secondary school level, we deal mainly with one-dimensional motion, but at college level, we have to deal with two-dimensional motion. Two-dimensional essentially means that there is the x and y coordinates to deal with. There's the x and y direction to deal with. Okay, let's give an example. But before that, we should recap the four kinematics equations that we have dealt with in a previous video. Okay, so just for some recollection, there are four equations. The first one being the simplest one, which comes from the definition of acceleration, and that gives me v equals to u plus at. In case you have forgotten, v stands for final velocity. Let me label it properly. U stands for initial velocity. A, of course, stands for acceleration. T stands for time, and S stands for displacement. Right? Stands for displacement. Okay, so the four kinematics equations would be v equals to u plus at, v squared equals to u squared plus 2as, s equals to half u plus v times time, and s equals to ut plus half at squared. Okay, so let's give an example. So, for example, you are in archery, right? You're standing on level ground. You're trying to shoot an arrow with a bow, right, at a certain degrees, so that it will undergo projectile motion and it lands on the target board, right? So you have a target board with a bullseye being placed on the ground. Okay, so let's give you some quantities to deal with. So, for example, if the distance here, let's say it's 100 meters, the angle of projection, theta. Okay, so let's define theta. Theta, it's say 30 degrees. Right? Okay, so the question could be, how long is the journey of the arrow? How long did it take for the arrow to hit the board, right? And as well as what is I can't tell you. I can't ask about the speed at which it hits the board, because I need to give it to you for the initial speed. Let's say the initial speed it's 80. Let's say 80 meters per second, which is actually quite fast. Okay, just a hypothetical case. Okay, so let's try solving for the time, the unknown time. In this scenario, being a projectile motion, I have to divide the problem into two parts. One, it's to deal with the vertical direction of the travel. Okay, so for the vertical direction, what are the known quantities? Right, the known quantities would be my acceleration due to gravity, which is 9.81 meters per second squared. If you are used to using the round up figure of 10 meters per second squared, that's also okay. Okay, for us, let's use a more accurate value for the acceleration due to gravity, which is 9.81 meters per second squared. What else do I know? I know that my initial speed, now this is going to be tricky, my initial speed of the vertical direction, which means the vertical component of my initial speed, is not 80. You have to resolve it. Right? This is resolution of vectors. Let's just draw it at the side here. If I have 80 meters per second and I want to resolve it to the vertical and horizontal components of my velocity, I know the angle, it's 30 degrees. So this gives me 80 cosine 30 degrees for this component, and for this component it's 80 sine 30 degrees. Okay, I hope this is okay for you. This is base trigonometry, essentially, using sine and cosine functions. So my initial vertical speed, it's 80 sine 30 degrees, but I must have the habit of assigning a direction. Say if upwards it's assigned to be positive, right? That means the upward direction is assigned to be positive. Then which one should go to switching of sign, right? So 80 sine 30 is actually pointing upwards initially, so it's going to give you a positive one, right? But my acceleration due to gravity, it's downwards, right? Because due to gravitational pull, so it's going to be negative 9.81 meters per second squared. For the entire journey, this is a potential careless mistake or misconception by some students. Now, the displacement throughout the journey, what do you think? The displacement throughout the journey, what would it be? Right? It would be equal to 0, right? Because the arrow went up by a certain amount of distance and it came back down through the same distance, right? So the total displacement, initial versus final, it's 0 meters, right? Because it did not make any displacement vertically. It went back to the same height as before, right? So I am tasked to find my time. What do you think? Which equation do you think I can use now? Of course, let's go back to my 4 equations. I cannot use the second equation because there's no time component. Final velocity, we actually know the final velocity, but I'll leave that aside first, and I'll come back to it by showing you another method of solving. But in the meantime, this equation seems to be the best, right? S equals to ut plus half at squared. So let's just write out the equation here. S equals to ut plus half at squared. Displacement, it's 0. And it's equals to initial velocity in the vertical direction, sine 30, and multiplied by time. And I need to plus half and negative, this is very important, right? The negative sign, and t squared. Well, luckily for us, the left side is 0, so it's quite easy because you can cancel out the time, right? Just divide the time throughout both left and right of the equation, and to rearrange. So time, so let me write it here. Time, it's therefore equals to 80 sine 30 multiplied by 2, right? And divided by 9.81. 9.81, right? The negative sign is gone because when you bring this component of the equation over, you will achieve a negative sign, and you will cancel out, right? The 2 negative signs will actually be cancelling out. Right, so you just need to calculate this value, and voila, you have the answer in seconds. Right, so this is one way to solve projectile motion, where the body is shot at an angle above the horizontal. Okay, thank you very much. Next videos coming up soon. I could probably be doing the following chapter, or show you some more examples of kinematics in terms of projectile motion. Okay, thank you very much. See you soon.